Thank you for the lovely introduction. Appreciated it. Well, hi. How are you all doing? Good? Okay. In the back, thank you. I appreciate the methods of Aristotle, who is conversational. So despite it's me versus all of you, we will be having a conversation, okay? Great. So I wrestled with the title meaning I came up with it in about 30 seconds without a lot of thought. But what I came up with today is thinking outside the panel, how solar panel orientation and location influence power production, the local environment, and economic value. Now, I understand that there is not an engineering degree here, although I believe there's a kind of a trade program we have or something like that. So I've done my best to address this to a general audience, all right? And we're gonna talk about this, and I'm gonna help you understand a little bit about solar and the kind of research that I've done with solar. But ultimately, this is a story about people that I'm going to tell you today, because that's what research is all about, is people. Before I go anywhere else, I did want to introduce you to my family because I like them. So, yes, I grew up in Colorado where there are mountains. Okay, I don't know if you've looked around, but there are no mountains here. And I met my wife, Lenore, who's there on the right, in Colorado. I recently learned that Lenore is the name of a fabric softener in the Netherlands. So there you go. We have two kids, Blue on the left and Ivory on the other left. And I've depicted them both covered in mud because that is what they always are. They're very curious kids who love to just get out there and cause all sorts of havoc. I was going to put up a picture of them lighting hand sanitizer in a bowl on fire to try and make a homemade Bunsen burner. That's what I found them doing yesterday outside. So that's what I'm dealing with at home. Also, I wanted to show you my costume from Halloween. It's a dumpster fire. I was a dumpster fire for Halloween. I thought it was great. I tried to teach in it, but my arms could extend kind of like a T-Rex, so I couldn't write on the whiteboard, so that's as far as I got. Anyway, I'm from the University of Dayton, which is an hour and 17 minutes away with current traffic, and it is a private Catholic research university in Dayton, Ohio, founded in 1850 by the Society of Mary, known as the Marianists. We have 11,300 undergrad and grad students. There are schools for engineering, business, arts and sciences, health, education, and law. I've been there since 2019. First time I ever set foot in the state of Ohio was for my interview at the University of Dayton, and I actually love it here. Despite coming from mountains, I love the green, and honestly, I really like the people here. People in Ohio are down to earth, fun to talk to. Yeah. So I had a slide about St. Albert, so forgive me for going a little bit into him myself as well. Thank you for your comments. Some things I wanted to point out, full disclosure, I'm learning about Catholicism now that I'm at a Catholic school, but I had not heard of St. Albert before this lecture. But I learned a lot about him over the last couple of weeks. Some things that impressed me about him was he is a universal scientist. He, as was mentioned, it was a physicist and a chemist and a botanist and basically anything you could be, he was curious about it. And that was really my main takeaway was that he led with curiosity. And that is a thing I appreciate, having two very curious children who love lighters. He insisted that knowledge must begin with observation, which is something I really appreciated. Also, he knew a lot of people. I was impressed later in life. He acted a lot as sort of a negotiator amongst different groups of people, which I appreciated. Our theme for this talk is the common good. So what I wanted to do today was I wanted to speak to you about what I've done, but I wanted to kind of keep the spirit of St. Albert in the talk and show how curiosity is ultimately what led me to this podium, okay? Also, here's the deal. I think engineering lectures are boring. I know, because I give them for a living. I can tell you how many students fall asleep in class. It's too many. And I try so hard. I really do. So I want to visit this topic in the spirit of St. Albert by telling the story of me, an engineer who led with curiosity, and other engineers who led with curiosity, and the people I met along the way, and how I ultimately stumbled into a cause that is for the common good. I'm going to do my best to leave time for questions at the end. Yes. We're going to tell this as a story. We begin with the beginning, in which a career in spacecraft thermal control gets a bit off course. So, as mentioned, I graduated with my PhD in 2019. I was high flying because I got this cool tenure track job at the University of Dayton, and I was publishing these papers, and I made this funny looking thing, which was a spacecraft radiator that moved in and out, and I tested it at NASA, right? I took a picture there, and I thought I was so cool. And so I said, hey, I'm going to show up, and I'm going to develop leading technologies in spacecraft thermal control for, to change the world. You guys recognize that? COVID-19, right? So I started in August of 2019. COVID happened in, March, and they shut my lab down and turned off all of my startup funds. And they said, okay, actually, you can't spend any of this money. You can't use that lab we gave you. So I sat in my office and I said, well, my tenure clock is 5 years, and I don't know when I get any of this back. I need to pivot a little bit. Another problem was my colleague, Dr. Kelly Kissick. He ran for the hills. He didn't run for the hills, but he got a much better job offer at UC Irvine, and he left, leaving no one to teach the solar energy engineering class, which was going to start in 2 weeks. And my department head, bless his heart, thought it would be a good idea for me to teach it. And I said, I don't know anything about solar panels. And he said, that's fine. And he gave me a book. So I said, I will do it. So I started reading. I care about sustainability. It's a topic I'd been curious about. But it's one thing to enjoy, talking to your friends. But it's another thing to have people pay money to sit in a room and you tell them how solar panels work. Yes? So I said, yes, I will teach the solar panel class. Okay, before we get there, I need to teach you a little bit as well. So we're going to have a brief primer in which the audience learns a little bit about energy, orbital dynamics, and solar heat flux. Okay? Cool. Stick with me for a minute. I need a volunteer. You in the hat. No? Yes. What is your name? Jake? Okay. Do you have a phone on you? You do? I would like to buy your phone for $20. What? It's worth more? Huh. Worth. Can you define worth for me? You can't use the word worth in the definition of worth. Excellent. Would you say it's the value of something? Okay, what's the definition of value? Is it the worth of something? Okay, I agree. That's the best I can do. Thank you for volunteering for this. I volunteered you like they volunteered me, okay? That's how it feels. So, what? He did. He signed you up. So you'll have to take that up with him later. Yeah, so you don't want to sell me your phone for $20 because you insist it's worth more than that, which is fine, whatever. Your loss could be $20. I don't actually have it on me. It's a picture. I'm surprised how detailed of a $20 bill they put on the internet, honestly. That seems... Anyway, so worth and value. Intrinsically, we understand these things. We know what it means, but it's hard to define, right? If I take a squirrel and I put it on this podium and I put a $20 bill right here and I put an acorn right here, which one is it going to pick? I know which one you will pick. It's going to choose this unless it's a very smart squirrel, right? Why? Because the squirrel values the acorn more than money. And why is that? We know that $20 is worth $20. That seems like a lot of money. Well, maybe not anymore, but it felt like a lot of money at one point in time. So we understand value, and we assign something value. We need a common language, so we use currency, right? Dollar bills, we understand to express value. I can tell you the value of anything with a dollar bill. Like my time, I can tell you how much the University of Dayton is willing to pay me for my time. You can tell me how much you're willing to be paid for your time, or to go do a job for someone, or to buy a meal, or to not be in this lecture, right? There's a lot of things you could value, but the squirrel does not understand dollars. It understands something else. What is the currency that the squirrel is using to value the acorn versus the dollar bill? It must be a different currency than we understand. It must be one that a squirrel understands and that a snake and a tree and a rock understands, right? And that is energy. Energy is the currency of the universe. It's the mechanism by which we make fair trades. It's a measurement of the worth of something, okay? What's cool about energy is it follows two very distinctive rules. Number one, energy cannot be created or destroyed, right? All of you this morning ate cereal or a bagel or nothing for breakfast. That was me. And you are now using the energy in that bagel to walk and to talk or to sit and exist, right? And there's only so much energy in that bagel, and it can only fund so much of your life for the next little while before you really want to eat directly after this talk, right? And that's because energy is conserved. We can't take 1 joule, which is the unit of energy, and make that turn into a forever amount of energy. Just like you can't take $1 and make it turn into $5 magically. Imagine a world where energy wasn't conserved, right? You throw a ball and it goes like this, or you throw a ball and it shoots forward at like Mach 5. Everything would be completely chaotic. There would be no order to the universe. This ultimately is the law that tells us the universe is organized. Finally, rule number 2, the second law. Energy's usefulness decays with each transaction. Who is having a bad day today? Volunteer yourself. In the back. Do you want to tell us why, or do you need to keep it a secret? Oh, well, would you stand up for a second? Thank you. What's your name? Harley. Everyone, let's give Harley a big hand. You can do it, Harley. You're going to be fine. I'm also tired. I believe in you. Okay, you can sit down. Thank you, Harley. So we just used all of that cereal to clap. But what happened to the energy in our clap? Turned into sound, right? Yeah, and sound is energy. But where did the sound go? Well, it vibrated the air a tiny bit, and it hit the walls, which vibrated those walls, and we ended up making all these atoms just kind of vibrate a tiny bit more. In other words, we made the room get a tiny bit hotter. If we insulated this room, and if we clapped a whole lot, we could make the temperature go up a tiny bit, okay, from all of our clapping. Now, can we get the cereal back? Nope. Once we've vibrated little atoms, you can't eat tiny vibrations, right? It's lost. The usefulness of that energy is now gone. For us, anyway. It's been used. And that is the second law of thermodynamics, that entropy must increase. In other words, the utility, the usefulness, the value of that energy, according to us, goes down every time there is a transaction. Think inflation if we're talking about the currency we know, okay? Okay, sorry, this is a little small, but here's what I wanted to talk about. This is a flow chart of how energy flows through the entire Earth. Where does all the energy that the Earth gets comes from? The sun. That top left giant red arrow represents all of the energy coming from the sun. And where does it go? Well, it's reflected, it's absorbed by the atmosphere, it hits water and evaporates it, and it hits the surface and hits the surface. This is actually exergy, not energy, but just think of it as energy for a minute, okay? Some of it hits plants, which turns into photosynthesis, okay? So these arrows represent all the ways energy moves, and the circles represent where energy is stored, okay? The whole point of this plot is to show you that no matter where you got your energy from, it actually came from one place, the sun, right? Even if we're going to unbury some fossil fuels and burn them, the sun ultimately photosynthesized that energy millions of years ago, right? The only way we're getting energy not from the sun is if we're using geothermal energy, so that's from the heat in the core of the earth, or tidal energy actually uses the moon's gravity to generate energy. But for us and our environment, the sun is the source of energy, okay? So we better know something about the sun if we're going to talk about solar panels. So we're going to talk a little bit about the sun and the earth, okay? So we're going to, this is a video, yes? Okay, so here's the earth. The earth is tilted on its axis, correct, right? So here's straight up, the earth is tilted about 20-ish or so degrees, and it rotates around the sun. Now, a common misunderstanding is that the tilt of the earth is always facing inwards towards the sun. That's not true. The tilt of the earth remains pointed the same direction, directly at the North Star as it moves around the sun, okay? Which means that the earth, as it passes around the sun, is off normal. So what I've depicted here, this is from Wikipedia, not me, Wikipedia, is you can see the earth as it moves around the sun, and on the right, you can see the plane of the sun and how it passes over the earth. And so you can see we have 4 distinct events. The September and March equinox, right, when the day is of equal night, the length of the day and night are equal. And we have the winter and summer solstice, the shortest and longest day of the year. The winter solstice occurs exactly when the tilt of the earth is pointed directly away from the sun, as you see in that exact moment. That's when the sun's plane lines up with the bottom tropic latitude. Then as we move, we hit the spring equinox. In the spring equinox, the sun's plane intersects both of the tropics, as you see right there. And then as we move towards the summer solstice, the sun's plane will align with the upper tropic, as you'll see right there. Cool. So for us, what this means is we have seasons, right? The sun is closer to us in the summer, not closer, but we're pointed more towards it in the summer than in the winter. On the southern hemisphere, it's the exact opposite, of course. But what this means is that the sun has some strange behaviors when it moves through the sky, okay? On the right is a picture of the sun taken every hour, every day in Halifax, Nova Scotia, I believe, in the year 2014. And so you can see the path that the sun follows. The bottommost line is the sun on the winter solstice. The uppermost line is the sun on the summer solstice. And in the exact middle would be 2 lines that are overlapping, which would be the fall and spring equinox. Okay? So the sun, I don't know if you've paid much attention to the sun. I didn't until I taught this class. But pay attention to how high it is in the sky. Right now, it's winter. We're about a month away from the winter solstice. The sun does not get very high. Here in Ohio, we can expect it to get maybe 40 degrees above flat, okay? Now, in the summer, the sun will be really high in the sky, almost 85 degrees above the plane of the earth, okay? So the sun, and then it rises. Where does the sun rise? In the east, right? On the spring and fall equinox, yes. But every other day of the year, it rises a little bit to the north or south of the east. This is a polar diagram. It shows us the exact path of the sun every day of the year. So you can see on June 21st, the sun actually rises 30 degrees to the north of east. So keep that in mind next time you're lost in the woods and using the sun. Remember, it doesn't rise in the exact east. It changes as the year changes. In the winter, the sun rises 30 degrees south of east, so almost exactly to the southeast. Also, the length of the days change. You know this because you've been feeling it and experiencing it when the sun goes down at 5:30 p.m. and your children can no longer play outside and they start setting things on fire, right? So the length of the day shortens in Ohio by 4 hours in the winter versus in the summer, okay? The further north you go, the bigger the difference in the length of the day. Whew. Okay, so that's a brief primer on solar mechanics. Earth rotates around the sun's position in the sky changes with time. Next, let's learn a tiny bit about solar panels. So a solar panel is this magical kind of black thing that you put out there in the sun and light hits it and it makes electricity, right? So in a nutshell, how that works is you have a semiconductor, silicon, and that silicon has been layered in 2 layers and what we call doped. We've added something to the silicon. One of the dopings has made it so the silicon has too many electrons. A different doping makes it so that the silicon is missing some electrons. So you have one spot that's got extra, one that wants some, and you put them right next to each other. This is going to make a natural kind of pole. Then we allow photons or light to hit this surface. And if it strikes and is absorbed at that intersection, see that orange section called the depletion region, if the photon has just the right amount of energy, what's cool about a semiconductor is a little bit of energy causes an electron to bump up and exist in the conduction band, meaning it can travel now between atoms. Before it was stuck. So with a tiny trigger, we can make that electron move. Because we've layered these 2 silicons, there's a native voltage that pushes the electron away from where it used to be. And that electron says, ooh, I want to go back home, but there's this push. So what does it do? It goes on the great American journey, and it travels through the entire grid just to come back to that spot. It doesn't come back to that spot, but it's being pushed in the opposite direction, and we've generated power, okay? So that's how solar panels work, just a little bit. We need sun to shine on them, and we need sun to shine on them directly. So here is a panel with the sun shining straight down. If instead the sun is shining on the panel from the side, well, if I show you my hands, these look pretty big, right? But if I turn my hands, then to you, my hands are small if you think in 2 dimensions. So the size of my panel must be reduced. So I've shown how my panel's area has been projected to be normal to those rays, and there is now less panel that is seeing those rays. So as our panel moves away from being directly hit by the sunlight, then we actually are going to make less electricity. Now, this is a problem because what did we just learn about the sun? It moves in the sky, right? And we just learned about panels. They want to be directly facing the sun. So what do we do? What was that? Sorry, I couldn't hear. I'm going to assume you said, point them at the sun all the time. Who thinks that's a good idea? Oh, wait, we have an idea in the back. You like that idea? Okay, are you going to hold it and point it at the sun all the time? Okay, who is going to do that? Okay, I don't know. I like the idea, but we're going to struggle to make that happen, all right? We could make machines to do it, but machines cost money. And when it comes to energy, we care about money and doing it for cheap, okay? It's easier to just plant our panel on the ground and fix it at a spot. So where are you going to point it? If the sun is always moving in the sky, where would you point the panel to get the best amount of exposure? I sort of ruined it. But here you see my panel. If I point it so that the sun is exactly perpendicular to my panel at the fall and spring equinox, then in the summer it's slightly above, in the winter it's slightly below, and I'll actually collect over time the maximum amount of energy. At least that's what the solar industry would like you to think. We have now come full circle back to the question, right? I started teaching this solar class, and I had some students, and I got to this part of the class, and they said, but professor, is that actually true? They said, in the winter, it's cloudy, And in the winter, what did we just talk about? There's less sunlight, and sunlight is fuel. So shouldn't we actually tilt these panels slightly more down so that we collect more energy in the summer and less in the winter when there's not energy to be collected? And I said, oh, that's an interesting idea. So here I was, just barely learning about solar and keep like literally a week ahead of lecture. And they come to me like, what do you think about this? And I said, that is a good idea. Okay, we had our first idea, in which a scrappy band of researchers makes its first steps and its first mistakes. So those students were Sabin and Isa, shown here on the left. And they said, to us, it makes more sense to change the panel down so that it gets more in the summer. The industry standard is to tilt it at the latitude of your position. That is what makes the most energy. But they wanted to prove that wasn't true. So they got on the computer. Remember, this is when COVID was happening. I had no lab, I had no money, but I suddenly had 2 volunteers and a computer. And I needed to publish something. So I said, I have an idea. How about you guys get on this free website called PV Watts, which will tell you the amount of energy you get out of a solar panel for its tilt angle. And you write a code that's gonna ping this website 1,000 times. And I want you to run an optimizer and find the best tilt angle for every county in the United States of America. And we're gonna publish that. They said, okay. So remember, 2 problems with solar panels. Number 1, clouds. So on the left is the typical cloud cover average over the course of a year. Averaged over winter months. I'm sorry, this is winter cloud cover. And so blue is cloudy, red is sunny. You see Ohio right there? Super dark blue, that's us. Seasonal depression is coming, my friends. So we have all this cloud cover, and what's that gonna do for our solar? Make it less likely to generate in the winter, right? So what places are going to want to tilt their panels more? The places with more cloud cover. Likewise, if a solar panel gets hot, it actually generates less electricity. If it gets too hot, it stops altogether, okay? So some locations like Arizona, it's so hot in the summer that their production goes down. In the winter, they actually might make more energy, especially since there's no clouds. So our students took this data, combined it with PV Watts, and came up with a model that predicted the total energy you could get at the best tilt angle for every county in the United States. And here were the results. So first on the left is the total amount of energy you can get at the best tilt angle for every county. And it's clear that the Southwest is doing really well. These are, I've just given you relatives of low and high, so we don't need to worry about numbers too much. And then over here where we are, it's pretty dark blue. Seattle is terrible. There's just this section where there's just clouds all the time, right? So you can see that production, but then the question is, what was the best tilt angle? So over here, I've said low means closer to the ground, high means higher up, and you see this very definitive pattern. As we go up in latitude, our tilt angle wants to be higher up, right? And that's what lines it up with the equinox. But the question is the tilt angle at each county equal to the latitude of that county? Because that's what a solar installer will tell you to do. So we compared them. In this case, white, the color white represents that your tilt angle should be equal to your latitude angle. Blue represents it should be lower than, favoring summer collection. Red means it should be higher than, favoring winter collection, okay? Where the darker blue means up to negative 12 degrees. You want to move that panel negative, so 12 degrees below your latitude angle. So you can see, for example, in Seattle, Washington, 55 degrees latitude, I forget. You actually want to put that panel at about 42 degrees. So you're tilting it to severely favor summer collection. Likewise, in Florida, there's actually some red. And that's because there is cloud cover in the summer from hurricanes and not as much in the winter. And so it's better to actually make your panels in Florida point a little bit up. Likewise, in Arizona, the hot summer is still got more sunlight, and so it's best to just put it where you think it should go. You also notice that as you move up, it seems to get darker in color. So the higher you are, the more you should tilt down relative to your position. And that is simply because there's more daylight hours in the summer than the winter. Okay, I'm gonna try to move through these a little bit quicker. So then we said, hey, what if the idea of holding the solar panel, what if you take it and you just move it twice a year, once for summer, once for winter? There'd be an optimal summer and winter tilt. And we could take these two different lines, which represent the production in the summer and the winter, and combine them into that dotted line that's going to get optimal production. So we did that as well, and we found the best tilt angle for every state, because county was a little too much work this time. So we found every state's best tilt angle, and we found some states like Illinois and Pennsylvania and South Carolina, you wanted to make a pretty big change between them. Others, you didn't need to make much of a change. So we proposed this idea and published a paper about, so we published this in a paper, we published this in a conference paper, and then my student Sabin kept going. He said, okay, well, what about the space between the panels? And what about the way the panels are pointing? Like, there's so many variables to play with here. So we said, all right, well, how should we point the panels? South, southeast, to the east. And we did some optimization. We ran a bunch of studies. That's what those little dots represent. And we tried it in a bunch of cities this time. And we found that, sure enough, you want to space your panels as close together as possible until there's shading, and then keep away from that. So 2.5 meters was the right spot. You want to tilt them. In this case, these are bifacial panels, so our tilt was a little different, but more or less close to the latitude. And your azimuth, or pointing, you want to point south, because that's where the sun is going to be most in the sky. So I thought this was cool, right? And we published that as a conference paper. I had publications. I'm going to get tenure now, right? So we go and we present these, some conclusions. You know, the best tilt exists below the latitude. In Ohio, it's about 7 degrees below latitude. So instead of 40, you want 33 degrees for your best tilt. And if you change that tilt, that's really good, and you want to point it south. And we'd say this at a conference, and the people looked at us like, well, yeah, duh. Everybody knows that. Go look at the literature. So we looked, and sure enough, there's about 200 papers that all say the same thing, that had done the same thing. And, you know, I forgot to have my students do a thorough enough literature review. We still got it published, but they said, well, honestly, what sets the tilt is the zoning ordinances and wind loads. And honestly, it's the decision to buy solar is about money, not energy. That's why people get solar. And everyone's already published about this. So I was a little defeated, right? We are now entering the refiner's fire, in which questions that people actually care about are answered. So I came back from that conference and I said, well, shoot, I didn't think about things that actually matter to people. I'm an engineer, and here I am answering these basic questions everybody already knows. So I had this student named Jacob, and Jacob came to me, and he was doing this summer research experience, an undergraduate summer research experience. And I told him, I got to figure out what to do about money. Not like that, but solar panels and money and how to make them make sense together. And he said, well, I have an idea. I said, okay. He came back a week later. He'd made a whole model and had started writing the paper already. I was like, Jacob. We actually just published that paper last month. So, what was Jacob's idea? Here, I'm showing a few plots that represent the load, or the amount of energy that a building is using, okay? On the left is July, on the right is December, for different cities. We're gonna focus on Phoenix, which is the dotted line. So in Phoenix, there's a lot of energy used at about 5 o'clock, 6 o'clock. That's when your AC is really going in the summertime. In Phoenix, in the winter, there's more a peak in the morning at 8 a.m. and a peak in the evening when everyone's coming home and turning on lights and cooking food, okay? So why does this matter? And what does it have to do with solar? Okay, here is a view. I have solar panels on my house. Actually, I got them as a teaching aid. Not just for that reason, but they're fun. Anyway, on the left is a picture of my production and consumption in the month of July. Okay, so, I can use this. Here is the production of my solar panels as a function of hour, and here is the amount of energy I'm using. This is on June 21st, the summer solstice. You see that I'm making a lot of energy at noon, but I use most of my energy in the afternoon and evening. Is this a problem? Well, yeah, I kind of want to use my energy when I want to produce energy when I'm using it, right? Luckily, utilities let you do this thing called net metering. When I make too much energy, see, I'm making way more than I'm using, I say, hey, utility, can I give you some energy? In fact, I'll sell it to you. And they say, sure, I'll buy it off of you. So they buy the energy from my solar panels. And then later in the day, when my solar panels make less than I'm using, they kind of sell me that electricity back for free because they sold me some earlier in the day. So we do a little exchange of energy, okay? And Jacob said, that's fine, that works if they offer you a fair price on both exchanges. But what if they refuse to sell you electricity at the same price that they bought it off of you from? What if they sell it to you at double than what they buy from, right? And this is happening right now. So what we want to do in that case is instead of generating solar like this, we want to move our production to the right. We want to make more energy when I need it. Just for a visual, that's the energy I made yesterday. It snowed in Dayton, so I made 0 kilowatt hours. And I have no idea what happened at 9:30 in the morning, but something happened. I used a lot of energy. Anyway, I try to not look at this in the winter. Okay, why does this matter? Well, in Phoenix, they're going to charge you a lot more between 4 and 7 p.m. Your cost goes from 6 cents per unit of energy to 14 cents per unit of energy. And to make matters worse, see that? Oh, darn it. Oh, spoiler alert. On the bottom, they're going to charge you $20 times the number of kilowatts you use at a peak moment in the month. So if you turn on all your AC and all your lights in your stove, they're going to charge you for that, like $20 times however much you're using. That could be up to $100 a month as an extra charge on top of all the electricity you're buying. And guess what? They're not going to, if they buy solar off of you here for 6 cents, they're still going to sell you electricity here for 14 cents. So you lose money, right? You sell them energy for a low price. They sell it back to you for a high price. So in this case, what we want to do is point our solar panels in a slightly different way. These plots represent the azimuth angle, or which way we're going to point our panels, where 180 degrees is south, and the y-axis is the tilt angle. So in a normal case, this is how much energy we make. The most energy is made if we point south and are tilted at a little bit below latitude. Over here, though, is if we want to save money. So I started paying attention. I said, money. How do we save money with pointing our solar panel? And it turns out that if you want to save the most money, you actually want to point your solar panel to the west, about 30 degrees, okay? And you want to tilt it the same. Why to the west? Because that is going to line up your solar generation curve with the peak in your load. So Jacob found this. He wrote a paper about it. He even did some results to say, okay, how much should you let them sell it to you for? And so we did all these results. He also went through all these different cities to figure out how much you could save if you point them a slightly different direction. In the end, he found that if they buy and sell from you at the same cost, then you should just point your panels to get the most energy. But if the utility is charging you a different amount for buying and selling, then point it so that the solar is aligned with the sun when you need the energy the most from a money perspective. Okay? Went to the conference and they said, cool, but that's still not the reason people don't take on solar. There's environmental impacts. There's a lot of other things. I said, oh. So we had to think about even more things. We had to move outwards, and we had to think about application. So we'll talk through this last research project. So I teamed up with a biologist named Chelsea Prather and a chemical engineer named Amy Sirik. And then I found a student named Alex. And Dr. Prather said, hey, we noticed that bugs land on the solar panels all the time. And they think it's water. And they plant their eggs on the solar panels, which burn up and do not hatch. Likewise, the bugs burn up on the solar panels. So there's all these biological things happening. Likewise, under the panels, the ants are moving out from the solar arrays. And we don't know why. So we set up an experiment. We took these tiny watch buttons. Believe it or not, that's not a watch button. It is a temperature measurement device in the size of a watch button, and it will measure temperature and record it for years once you hit go. So you put it out there. So we made these little solar shields, and we deployed our watch buttons under the panels and in between the panels and outside of the panels. We wanted to see do the panels make the surroundings get hotter or colder? We did this over all 4 seasons at 2 different places, one a tracking array and one a tilted fixed array. This is winter data, so I'm actually going to zoom to summer. In the summer, what did we find? Well, this shows you all of the data. Of course, I don't expect you to pick anything up off these plots. On the right, you see U is for under, B is for buffer or outside the panels, and A is for aisle. And the thing I want to draw your attention to the most is right here. So in the summertime, the aisle is 4 degrees hotter than the buffer zone. And why? There's more shading there than in the buffer, at least we thought. Then I went there to look, and the region outside of the panels was overgrown with plants. But what was in between the panels? Smaller plants. So these plants are not growing as high, which is not shading the ground. So the ground gets hotter, and also we found that the water is evaporating more. So the ground is drier, actually. The air above the ground is drier in the solar array than outside of the solar array. So the solar array itself is impacting the environment and changing how these small bugs and even the mammals interact with the environment. These are a few more results from a fixed array. In this case, we found actually that the aisle that under the panels was cooler and between the panels was warmer, which was a unique result. Comparing the two, these blue lines represent the aisle. We found that for our tracking array, because there's more shading, it just does not get as hot for as long as a fixed array. And so we showed that there's a difference in how the different types of solar arrays impact the environment. And those were some conclusions. And finally, conclusions people said, oh, now that's an interesting takeaway. So we learned that tracking panels decrease the temperature within the array, that fixed solar panels change the temperature in the array depending on the season. There's a wider variation in that temperature. The humidity is less affected, but less evaporation occurs. So then we had the last idea. Well, shoot, if there's more shading, could we grow plants there that are more susceptible to like burning in the sun? So gaining momentum, in which the team actually finds a place to contribute to the common good. We are now embarking on this long journey. I've gathered all these people with an interest in solar, and we finally found a place, agrivoltaics. Agrivoltaics is growing crops under or in between solar arrays. In Greene County, which is right next to Dayton, there was a large solar array proposed that was ultimately shut down by the community because they didn't want solar on good farmland. I can understand that argument. So the new argument is, well, what if we put solar spread out on farmland? The advantage is farmers actually earn money off of this and can afford to farm, as farming is a net loss job these days. So we formed what I'm calling the SOLAS group, the Solar Applications in Co-located Environments. And we're now forming and submitting proposals to do real studies of what plants should we plant under these solar panels, and what is the best yield, and financially, what makes the most sense? How close or far apart should we put these panels? How high above the ground? So many things to think about, so much curiosity. So my final takeaways is technical portions of solar are solved. People know how to tilt them and where to point them. I showed you the things I found out that other people already knew. Solving solar penetration is not just about where to point them. It's solving all the problems. It's policy, it's finances, it's biology. Leading with curiosity and working with a great team drives innovation and moves improvements towards the common good. Finally, I think my main takeaway is every good problem worth solving is not solved by one person. I've depicted some of my team members. I didn't even get to half the people I've worked with. But ultimately, I think St. Albert would agree that it's best to work together to solve problems like this. So thank you. I've gone, I think, a little bit over time, but I'm happy to answer questions if there is any.